Hello. So this is going to be episode 2B. We're going to be talking about episode 2B of second order equations. So this is going to be chapter, I think we're chapter 5 here. So what we're going to be looking at is the linear second order differential equations where we have two conjugate roots. So I'm not going to give an explicit example, but let's suppose we have our characteristic equation, a plus br plus c equals 0. And we do the quadratic formula, a equals, okay, negative b plus minus b squared minus 4ac over 2a. What do we get? And then this is going to give us something, so it's going to give us x plus or minus I y. Okay, it's going to give us something like that. And maybe actually I'm going to avoid x and y because that's going to use something fancy, alpha plus or minus I beta. Okay, so this is R. So what can we do? And obviously we have y is equal to e to the power of rt. So what do we do here? Well, first of all, let's just actually write this explicitly. Y is equal to e to the power of alpha plus or minus I times beta. And we can split this up. So this becomes e to the power of alpha times e to the power of plus or minus I beta. And if you remember Euler's identity, e to the power of I theta is, or I guess it's a phi, is equal to cosine of phi plus or minus I sine of phi. Oh, and actually I forgot there's a t here, or an x, if y is a function of x, right? So as a function of x, oh, I put a t in there earlier, so we'll just go back to using this t here. So alpha to the power of t plus or minus beta t, right? So we can use Euler's identity here, right? E to the I theta is cosine theta plus or minus I sine theta, right? And using that we can basically rewrite this equation for y. So y is equal to e to the alpha t times cosine beta t plus or minus I sine beta t. Yeah, right. But this isn't helpful exactly, at least not yet, because we still have the issue. So obviously a y is not exactly plus equals. We have a y1 and then a y2. So y2 is going to be this. Let me just grab that, pop it here, and then I'm going to rewrite some of this stuff. All right. So we have this y1 and then this y2, right? So we have two separate solutions. And then if you remember, because of superposition, any solution y is a linear combination of y1 and y2, right? Or the span of these two functions. So we talk about that in episode 1 of this chapter. So, well, what can we do here? Because we have this complex. We want real solutions. So we want to get rid of this complex part. So how do we do that? So obviously there's a few things we can do here. So the first thing is if we take y1 plus y2, we're going to get 2e to the alpha cosine beta, right? Because these cancel out. So we have one, right? So we can put this to one equation here. So I'm going to call this u, or not u, f, just f, simple f of t. Actually, sorry, I'm bad with these. Mu of t is equal to 1/2 y1 plus y2, right? Or just e to the alpha cosine beta t. And then, so in this case, we have the this is basically the same as saying C1 in our equation is equal to, sorry, C1 is equal to 1/2. Right, so we have this C1 here. Now, if we do the opposite, we have y1 minus y2. You get the opposite. We get 2i e to the alpha t sine beta t, right? So we do the same thing, and then what we're going to find, we have c2 is equal to 1 over 2i, right? So I'm going to call this eta of t is equal to 1 over 2i y1 plus y2. And then with and then what we can do is, using these sort of using these descriptions again, not descriptions but substitutions, we can pretty much rewrite our equation with y is equal to c1 mu of t plus c2 eta t. And so now we have, because if you notice this is real, this is going to be, when we divide by 2i, this becomes, I didn't finish writing it out, e to the alpha t sine beta t, right? So we get this y equals c1 mu t plus c2 eta t, and this actually just becomes c1 cosine, or e to the alpha of t times c1 cosine of beta t plus c2 sine beta t, right? So all of these steps here, we don't have to do that anymore, right? All we need to remember is this half here. Once we get, once we find this R, which is, you know, a conjugate pair, then, so once you find a conjugate pair, then we can just skip straight into this equation for the solutions of our differential equation for y. So hopefully that wasn't too much. Maybe I'll go into an example in the next video. So see you then.